Welcome to Module 1, Part 2. In this segment, we will be discussing Earth's composition and types of plate boundaries. So let's begin with the theory of plate tectonics. In our previous module, we discussed continental drift hypothesis. Following World War II, oceanographers learned a lot about the sea floor, and these developments eventually led to the theory of plate tectonics. For example, due to the invention of sonar, oceanographers learned that we have an oceanic ridge system that winds through all of the major oceans. We learned that there is no oceanic crust older than 180 million years old through the Ocean Drilling Project. And through this same project, we also discovered that sediment accumulation in the deep oceans was relatively minor. This led to the concept of seafloor spreading. So along the crest of the ridge in the middle of the oceans is a canyon-like feature called a rift valley. Seafloor spreading is the mechanism that operates along the ridge to create new ocean floor. Seafloor spreading as a mechanism was first proposed by Harry Hess in 1962. Harry Hess was a naval officer who used sonar during World War II. Now, spreading rates vary depending on the boundary where the spreading is occurring. The average global spreading rate is 5 centimeters per year. But the Mid-Atlantic Ridge, for example, has a spreading rate of 2 centimeters per year. That's about as much as your fingernails will grow in a 1-year time period. But the East Pacific Rise has a spreading rate of 15 centimeters per year. And we will discuss why these differences occur later in the lecture. Just a little bit about Earth's composition. Earth has a rigid lithosphere which overlies a weak asthenosphere. So the lithosphere is Earth's strong outer layer. That's where we live. The asthenosphere is a hotter, weaker region of the mantle that lies below the lithosphere. And because of the differences in physical properties between these two layers, the lithosphere, which is cold and brittle, is effectively detached from the hot asthenosphere. Now, just as a side note, the asthenosphere is not molten lava or magma. It is just very hot rock that flows with what we call plastic flow. The lithosphere is broken into approximately 24 smaller sections called lithospheric plates. Now, when I say 24, I'm talking about the major plates on Earth. There are many, many more small or minor plates on Earth's surface. These plates are in constant motion. And in this illustration, you can see, for example, the North American plate, the South American plate, the African plate, the Pacific plate. Some of these plates contain oceanic crust and continental crust. Some of them, such as the Pacific plate, contain only oceanic crust. Most interactions among individual plates occur along their boundaries. We have three main boundary types: divergent plate boundaries, which are constructive margins where new seafloor is formed, and these are plates that move apart from one another in opposite directions. Convergent plate boundaries are destructive margins. These are where the plates move together and they destroy crust. And then we have transform plate boundaries. These are what we call conservative margins. In a transform plate boundary, the plates basically grind horizontally past one another without the production or destruction of crust. These can also be called transform faults. We'll begin by talking about divergent plate boundaries. New ocean floor is generated as two plates move apart. Basically, they split apart and magma wells up and then cools and creates new crust. Most of these divergent plate boundaries are located along the crests of oceanic ridges, but some actually cut through the continents. Oceanic ridges are where seafloor spreading occurs. So along these well-developed divergent plate boundaries, such as the Mid-Atlantic Ridge, the seafloor is elevated, forming this ridge where the two plates move away and magma wells up. In this illustration, you can see a good cartoon, if you will, of the sites of seafloor spreading. In the lower illustration, you see the Mid-Atlantic Ridge and a little arrow pointing toward the spreading center. This is the Rift Valley. And on the top, you see a close-up of what the Rift Valley looks like. So you have two plates moving apart from one another. So, for example, the African plate and the North American plate, with a Rift Valley in the middle where the plates are thinning and pulling apart, and where magma wells up from the asthenosphere through the lithosphere and breaks through to the surface, creating new crust. I mentioned continental divergent boundaries. When this occurs within a continent, we call it continental rifting. And basically what happens is a landmass will split into two or more smaller segments. A continental rift is an elongated depression which will develop within the region where the divergence is happening. A good example where this is happening today is the East African Rift Zone. Here you can see on the right a map of the East African Rift Zone. So if you look at focus toward the middle, you'll see the Afar Triple Junction. This is the fastest diverging place on Earth. Eventually, in a few tens of thousands of years, this area will thin so much that the Red Sea will encroach into the Afar Triple Junction area and start forming a new ocean basin. On the left side, you can actually see a continental rift. So it's a deep valley caused by thinning of the crust and normal faults that cause downdropping of the surface. A lot of these rifts in the East Africa Rift Zone eventually form lakes like Lake Albert, Lake Edward, Lake Kivu, Lake Tanganyika. These are all long linear lakes in the Eastern African Rift Zone. The second type of plate boundary are convergent plate boundaries. And these are where two plates will move toward each other at what we call a destructive plate margin. And basically what happens is the older portions of oceanic plates are returned to the mantle through a process called subduction. Deep ocean trenches are the surface manifestation produced at a subduction zone. So examples of these deep ocean trenches are the Peru-Chile Trench off the coast of South America, the Mariana Trench in the Pacific, and the Tonga Trench, also in the Pacific. There are three types of convergent boundaries. The first type is the oceanic continental convergence. And this is where we have an oceanic slab converging or moving toward a continental slab. So what happens in this case is the oceanic slab is denser. Think of it like this. It's basically has been soaking up water and collecting sediment, plus oceanic crust has a lot of iron and magnesium. So it's denser than continental crust, which is lighter and floats on the surface, if you will. But this dense oceanic slab sinks beneath the continental block into the asthenosphere. At a depth of 100 to 150 kilometers, partial melting occurs because water from the subducting plate mixes with the hot rocks of the asthenosphere, and this generates magma. The resulting volcanic mountain chain is called a continental volcanic arc. Examples of this include the Andes Mountains, and in North America, the Cascade Range up in Washington and Oregon. Here you can see a picture of Mount Hood in Oregon. It's a volcano formed because of oceanic continental convergence and partial melting. In the illustration below, you can see how the subducting oceanic lithosphere gets to a certain depth and it begins to melt because water driven from that subducting plate basically lowers the melting temperature of rock and triggers melting. That molten rock rises up, punches through the continental crust, and creates a volcano. And we call this, again, a continental volcanic arc. So the Cascade Range, which includes Mount Rainier, Mount St. Helens, Mount Hood, they are all part of this continental volcanic arc. The second type of convergent plate boundary is oceanic-oceanic convergence. And this is when two oceanic slabs converge or move toward one another and one descends beneath the other. Now, which one is going to end up descending? Basically, the older slab will descend beneath the younger oceanic slab because the older slab has had longer time to soak up more water and gain more sediment, so it becomes denser. As with oceanic continental convergence, partial melting initiates volcanic activity. And the geologic feature that it gives us is called a volcanic island arc. And examples of this include the Aleutian Islands off the coast of Alaska and the Mariana Islands. In the top photograph, you can see a picture of one of the volcanoes in the Aleutian Island chain. And in the lower illustration, you'll see a map that shows this volcanic island arc. Notice it's arc-shaped. And the little red triangles show all the different volcanoes along the Aleutian Island chain. Something else I want you to notice is the darker purple line that's right below the volcanic arc. This is the Aleutian Trench. So remember I said that a surface expression of a convergent plate boundary is a deep ocean trench. And deep ocean trenches are among the deepest places on Earth. Continental-continental convergence is the third type of convergent plate boundary. So with continued subduction, eventually two continents can be brought together. Now, continental crust is much less dense than oceanic crust, and it's more buoyant, so it cannot subduct. So when two continents collide, the resulting collision produces mountains. Examples include the Himalaya, the Alps, and the Appalachian Mountains. Here's an example of the Alps continental-continental convergence. The third type of plate boundary is the transform plate boundary. These are where plates slide past one another and no lithosphere is created or destroyed. Most of these transform plate boundaries join two segments of an oceanic ridge system along breaks in the oceanic crust, which are known as fracture zones. Transform faults can also move ridge crests towards subduction zones. There are a few transform faults that you may be familiar with because they cut through continental crust. A prime example is the San Andreas Fault in California. That is a transform boundary between the Pacific Plate and the North American Plate. Another is the Alpine Fault of New Zealand. So here you can see an illustration of where most of our transform faults occur. And they offset segments of a spreading center, producing almost a step-like plate margin. And they basically help the divergence slide past one another. And you can see in the inset a fracture zone. And basically they're really long, narrow, kind of scar-like features in the seafloor. And they're roughly perpendicular to the offset ridge segments. They actually have an inactive zone, and then the transform fault that's active, and then another inactive zone on the opposite side. So as the divergence continues at the mid-ocean ridge and they move further away, the outer edges become inactive. This is the end of Plate Tectonics Part 2. In Part 3, we will look at evidence for plate tectonic theory and the mechanisms for tectonics, as well as how supercontinents form.